what we see here is that they're both the same. So both of these periods are the same. They're basically the exact same thing. And so if we look at that and we take, what we can do is we can take this F and I put it in for F here. I get 2 pi over 2 omega sine theta. And omega is 2 pi over 24 hours. So I can put that in here for omega. And so when I do that, I see that I've got 2 pi over 2 times 2 pi over 24 hours sine of theta. And so I can go ahead and cancel 2 pi with 2 pi, and the 2 and 24 gives me 12 hours, but it's in the denominator of the denominator, so I can put that up on top. So I end up with 12 hours over sine theta. And so what I see is that the period of an inertial current and the period of our Foucault pendulum, those are the same. And this is called our inertial period. So that's what our inertial period is. It's the same for both. Okay. So that's how we can find our inertial period. We can do it with either 12 hours over sine theta, or we've just figured out it's the same thing, 2 pi over F. And again, it'll be a slight, if we aren't careful with our sidereal day versus our solar day, we will have a slight difference in calculation there. All right. So these inertial currents, we know that the acceleration must come from the only force acting on the water parcel, Coriolis. And so we saw that the acceleration in the x direction, which we, I'm sorry, that is incorrect there. That should be, so the acceleration in the x direction would be du dt. And I'm not sure I have it there as dv dt. Make that a u. There we go, du dt. And the acceleration in the x direction is du dt. And the centripetal acceleration is v squared over r. And so that's because the acceleration, the centripetal acceleration is v squared over r. And so we know that the acceleration in the x direction is v squared over r, and that must be equal to v times f, because this is equal to our Coriolis, which is v times f, and we're doing in the x direction. And so what we can do is we can find the ratio of the acceleration terms, which is in this case our du dt term, which equals v times f. And we can take a ratio of this du dt, which is going to be equal to, which is our v squared over r. And we're going to take a ratio of v squared over r to v times f. So we're going to ratio those. So I'm going to put that one on top of the other. So I put v squared over r over v times f. And now I see that I can go ahead and cancel one of my v's. So I'll have just one v, and this r will now be in the denominator. So I end up with v over rf. And this right here, if we look at it in the numerator, v, the units of that are meters per second. And in the denominator, radius is in meters. And f is going to be, that's a frequency, it's in per seconds, s to the minus 1. And so we see that we have our meters per second will cancel with our meters per second. So we have no units. This is a dimensionless parameter. V over RF, this is our Rossby number. The Rossby number is the ratio of the acceleration over the Coriolis. So it's the ratio of the acceleration terms over Coriolis. It's V over RF, where V is our speed. L is another way to write that. That's just a length, some length in the horizontal length scale, whatever the horizontal length scale of our motion is. V is the velocity, and F is the Coriolis parameter, which is just based on where we are, what latitude we're at. All right. So I have some more questions. Oh, no. So if the Rossby number is greater than 1, that means that V is greater than L times F. That means that our acceleration is greater than Coriolis. So if the Rossby number is much greater than 1, then the Coriolis term is not very big and we can ignore it. So we can just say, oh, we got a big Rossby number. That's what most of the things have been like that you've seen so far ever in any physics problem. We've just said it's got a big Rossby number. We're not going to worry about Coriolis. So that's what you've seen so far, is having a big Rossby number, something that's much, much bigger than 1, where the velocity is much bigger than the length scale times the Coriolis parameter. Now, if the Rossby number is about 1, and that's what we were just looking at, that's an inertial current. If we have an inertial current or something where we have a Rossby number of about 1, that means that the acceleration terms are about equal, right? So in this case, the acceleration terms will be about equal to the Coriolis terms. So that's what that tells us, if it's about 1. So if they're about equal to 1, then in that case, both the acceleration terms and the Coriolis terms are of the same order of magnitude, and so both must be considered. Now, if the Rossby number is much less than 1, that means that in that case, Coriolis is going to be, so that means that in that case, we've got the denominator is going to be the bigger term. So our denominators are bigger term in that case. So in that case, Coriolis is bigger than our acceleration terms. And so Coriolis in this case must be considered. And the acceleration terms are not very big. And in that case, we can ignore the acceleration terms. And that is the case for most ocean flows. So most ocean flows, we're going to have a really small Rossby number. So Rossby number will be very, very small. We'll need to consider Coriolis, but we won't need to worry about the acceleration terms.